Here we have a list of different differential equations. Here they are. Woo, those are differential equations. And these are their solutions. This is no, this is on page 502. I'm not going to wait for you to write these down. So this is a differential equation right here. Notice that it has the y inside of it. That's kind of weird. This one is a differential equation. It's using a t instead of an x. We can write this one as dy over dx if we wanted to, but we're using y prime instead. And this is also a differential equation. Look at it, it says double prime on there, and the y is there. Oh, that's interesting. And these are the solutions. These are called general solutions. They're not specific solutions because they have c's. In order to find specific solutions, we must find the c's. Check these out. Here's a differential equation. It's of the first order. And this one is also of the first order. And this one is a second order. This one's a third order. It's only the order is dependent on how many primes it has. The highest amount of primes. And here we have linear, nonlinear stuff describing these. But right now it's only important for you guys to know which order they are from. Does anybody else have that picture in their head, the speech? No? Alright, so we're going to separate this right now. To separate, we're going to get all the variables that are the same on one side, and then we're going to find the general solution. Okay, so we got negative x equals 0. Okay, so get the x on the other side. So we're going to add x to both sides. So it's going to be an x over here. So we have an x right here, and on this side we have a y dy over dx. Now, to get the dx over there, it's kind of like we're multiplying by dx, but not really, but we're going to write it anyways. And then we have y dy equals x dx. Now, to solve this, hey, stop that. To solve this, we're going to take the integral of both sides. Wow, that's a horrible integral sign. That one's okay. I'll help you out right there. Okay, so the antiderivative of y is y raised to the second power, and then we're going to have to divide by 2, which is the same as multiplying by 1/2. And then I'm going to say plus c. And we have to have a plus c because there's no lower and upper bounds. This is a general antiderivative. So then we do the x, we get the same thing. We get x to the second power times 1/2. Now, there's supposed to be a plus c, but I'm going to say plus d right now because we need to differentiate between this constant and this constant. Now, what you're supposed to do after you do that is you're supposed to get the y value alone. Write this in terms of x as a function. So I'm going to move this c to the other side by subtracting it. And what is a constant minus a constant? Oh yeah, another constant. Okay, so we have plus c. I'm just going to have a c there now. What just happened? I know, that's kind of weird. Then we have 1/2 and we have x squared. Let's multiply everything by 2, shall we? We shall. What's 1/2 times 2? Oh no. Okay, and 1/2 times 2? Oh no. And so we have x squared. And then we have c times 2, which 2 times c. Wait, what is 2 times c? Oh yeah, it's another constant, so I'm just going to leave c right here. Okay, it's almost like the c just keeps eating everything and it just stays the same. How do I get that y alone? Yeah, we're going to square root the dude. Whenever you square inside of an equation, you need to have a plus or minus right there. So I have x squared plus c. Interesting. That is your general solution, and that answer is not linear. Okay, now I want to show you guys something. Now, this is analytically solving it, or algebraically. I've seen both words used for the same thing. I want to show you guys how to represent this as a graph. How do you represent it graphically? We're going to make these things today. But let me first get the dy over dx alone. So I have y times dy over dx, and on the other side I have an x. To get that y over to the other side, we would divide, right? So we would divide by y, and this y wouldn't be here anymore. So dy over dx equals x over y. So here's this cool little thing that somebody created I'm going to use. I'm going to write this as, let's see, what is that? It was x over y, right? Yeah? Okay. So this is called a slope field graph. You see this little point right here? I can move this point around, and you can see what the slope is at any point. That's kind of weird looking, huh?
Yeah.
Okay, now I'm just showing it to you guys for the first time ever. I don't expect you guys to understand what's going on. I just want you to see how cool this looks. Now, I want to throw in our answer that we got. Do you guys remember the answer that we got? What was it?
Like the first
Quick.
one we did?
Yeah, yeah.
It was y
Oh, it was square root, right?
yeah, y
Square root.
minus x.
X squared, right?
Yeah.
Squared. And then we had plus c. Plus c. Okay, so plus c is just a constant, right?
Right, right.
Well, let's go ahead and throw our c in there. Okay, do you guys see anything that's missing from my my equation right here? The plus or minus. Now, the function can't be both at the same time. Right now, it is plus. Let me show you guys what the minus would look like. I put a minus right there, square root x squared, and I'll say plus c again. Okay, do you guys see anything interesting on this graph now? Let's make this projector mode. Oh, it's already on projector mode. Okay, is it? Do you guys see anything interesting? Like, look at those lines. Here, talk to your neighbors right now and discuss anything you see that's interesting. Okay, now keep watching it. I'm going to change my value of c. Right now, c is a 1. And we don't know the exact value of c, which is why this is called a general. These two are called a general solution because we don't know the exact value of c. If I change c, look what happens. Whoa, you guys, it's like really exciting, huh?
Oh my god.
So what you guys are hopefully noticing is what Nate is noticing. You see the little lines that you see everywhere? These lines that are continually changing because our constant is continually changing are following those lines. You never see one of those lines disagreeing with our curve. They're always agreeing with it. So the differential equation gives us all those little lines. It gives us a slope field. And then our solutions give us specific curves, like these ones that you're looking at right here. Now this is an interesting curve because it has a plus and a minus when you solve for it. But anyways, this is the differential equations. Now when we find an initial value, what we're doing is we're finding an exact c, and then you're finding exact curves for a specific solution, a unique solution. Differential equations.